Hi, let us continue with our discussions about the design of reinforced concrete peg footing subjected to axial loads together with the moment acting in the major axis. So far we have done proposing the dimensions of the peg footing. This is determined on basis of the surface soil pressure due to the prescriptive methods that is being used in the design of the foundations. According to the prescriptive methods, proposing a suitable size for foundations will be based on the serviceability limit state. Therefore, we will need to calculate the soil pressure of the foundations based on the surface load. This shall include the influence of the axial loads, the self-weight of the peg footing, as well as the moment acting onto the peg footing. Because of the moment acting in the major axis, the soil pressure in the major axis redistributes. This results in a slight increase in terms of the pressures at one end, resisting the moment, whereas a slight decrease in terms of the soil pressure at the other end. As a result of the uplifting response caused by the moment. Because of this, you're going to expect the soil pressure, instead of being equally distributed throughout the contact surface area, it is now behaving like a trapezoidal force. You need to also calculate the soil pressure in the minor axis. Since there is no moment in the minor axis, you will expect a uniform stress due to the soil pressure in the minor axis. And then you calculate the pressures and check against the soil bearing capacity. The soil bearing capacity in this case is 200 kN per meter square. You're going to make sure the soil bearing capacity is not exceeded before you can proceed with the structural design. Once this is done, we are entering into the structural design. According to the prescriptive method, the structural design will have to be based on the ultimate limit state. Specifically, we are talking about the moment as well as the shear. You need to provide sufficient reinforcement bar in order to ensure the design peg footing can withstand the moment as well as the shear caused by the soil pressure. With that, we need to first calculate the soil pressure at the ultimate limit state. We will use the same equations to determine the soil pressure, except that now the loading it will be based on the ultimate loads. This includes the ultimate axial loads, which is given in these questions is 1000 kN. And then the self-weight, which is calculated from the proposed size of the peg footing. Use the volume, multiply the unit weight, which is 25 kN per meter cube. Since we are talking about the ultimate limit state, that means we will need to multiply the self-weight with the factor of safety for the permanent actions, 1.35. The whole thing here divided by the area, which represent the contact surface areas of the base of the peg footing. Multiply the HF with the BF. And then next, you need to consider the effects of the moment. You have the ultimate moment multiply the y, centroid, and the I, moment of inertia. You may use the same y and the I that you have calculated earlier on for you to determine the soil pressure at the submissivity limit state. The geometrical properties, it will be the same. Only that you need to use the ultimate moment, which in this case, the ultimate moment, it will be 150 in the major axis and 0 kilonewton meter in the minor axis. Substitute the value into the equations, you get the soil pressure in the major and in the minor axis. Same thing, because of the bending moment in the major axis, the soil pressure at the ultimate limit state redistributes, leading to one end to have a higher stress and at the other end will be the lower stress. As for the minor axis, because there is no moment, we assume the stress it will be equal throughout. Having the soil pressure determined, we will use this for us to determine the moment and the shear force. In order to do so, we will need to first get some dimensions, as well as to get the soil pressure at certain locations, particularly the soil pressure at the surface of the column. Why is it so? Because later the moment it will be acting on the surface plane of the column. Same goes to the shear force. Now we're going to determine the dimensions Z1 and the Y1. Z1 represents the dimensions from the column face to the edge of the peg footing in the major directions, whereas Y1 represents the dimensions in the minor axis. How do you determine the Z1? You know the width of the peg footing in the major axis, which is 2.4 meter. You also know the width of the column in the major axis, which is 300 mm. Take the foundation width minus the width of the column divided by 2. That gives you Z1. You will do the same for the minor axis to determine Y1. Your width of the peg footing in the minor axis is equals to 2.2 meter. Your width of the column in the minor axis, which is equals to 150 mm. Use the width of the peg footing minus the width of the column divided by 2. This you get your Y1. Next, you will need to determine the soil pressure at the column face. In the minor axis is easy. Since that you don't have any moment, the soil pressure it will be the same throughout. That means this Py here it will be the same as the other ends, equals to 208 kilonewton per meter square. As for the Pz here, you will need to do some interpolations. P max in the z directions is 279 kilonewton per meter square, and then P min z it will be 136.9 kilonewton per meter square. Assuming it is linearly distributed, do some interpolations to determine the Pz here. That you will obtain 216.8 kilonewton per meter square. Having this obtained, you are good to go to determine the moment acting on the column face. To get the moment, you need to first find the resultant force due to the soil pressure, and then use the resultant force multiply the lever arm to the column face. In the major axis, The soil pressure is in the form of trapezoidal shape. The trapezoidal shapes, it will be the combinations of a rectangular stress and the triangular stress. The rectangular stress, it will be due to the PZ, which is 216.8. Use PZ 216.8, multiply the Z1, you get your resultant force F2. This resultant force will happen at the centroid of the area, giving you a lever arm of x2, which is half distance of the Z1. Use F2 multiply x2, you get the moment due to the rectangular soil pressure. And then you need to determine the resultant force due to the triangle stress. First, find the area of the triangle. You have the width, which is equals to Z1. You need the height of the triangle. This is calculated based on the differences between P max Z and the PZ. Use 279 P max minus PZ 216.8. That gives you this height. The area of the triangle, it will be this height multiply the Z1 multiply half. Standard equations for the triangular area. This will give you a resultant force F1. And then this F1 will be located at the distance of 2/3 of the base of the triangle from the column face. This distance is equals to x1. How do you determine x1? You use Z1 here, which is 1050, multiply 2 per 3. That will be the lever arm x1 for the triangular force. From there, you will be able to determine the Planck moment in the major and the minor axis. This is calculated based on the F1 multiply x1 plus F2 multiply x2. It is noted that the stress, it will be uniform throughout in the minor axis. That means while calculating the moment in the minor axis, there is no triangular shape here. From there, you will be able to obtain the moment acting due to the single plane. The unit, it will be the moment per unit meter as a result of the single plane pressure. This single plane moment will need to be converted into the total moment by multiplying the width of the moment. Your total moments equals to the moment multiply the width. You will need to calculate both for the major and the minor axis. Only that you will need to be careful with the B that you use. Based on the dimensions of the peg footing proposed, you can imagine in this way. The major axis, it will be at the longer span. The soil pressure, it will be something like this. Now, the Planck moment here will need to be multiplied with the width of the peg footing, which in this case, the B, it will be 2.2 meter. This is as far as the major axis is concerned. As for the minor axis, we are looking at the peg footing from the other side. The soil pressure, it will be uniform throughout. And using the Planck moment, you will need to multiply the width of the peg footing. And this width, it will be the 2.4 meter. What you see here, To calculate the total moment, the B you use in the major and the minor axis are not the same. You will need to choose the right B so that you get the correct total moment. If you find difficulty to determine the correct B, I would recommend you always sketch and imagine the peg footings in 3 dimensions. Only then you can correctly determine the B. Next, we will need to determine the effective depth of the peg footing. We need this effective depth for us to calculate the moment resistance given by the reinforcement. There will be 2 effective depth D for the major and the minor axis. The major axis, it will be more critical. Therefore, in order to maximize the contributions of the reinforcement bar in moment resistance, we will lay the main reinforcement bar closer to the soffit of the peg footing. This will be the formulas to determine the effective depth in the major axis. Get the thickness of the peg footing minus the concrete cover minus the half size of the rebar. Since the effective depth is referring to the distance from the top surface of the peg footing to the centroid of the reinforcement bar. The thickness of the peg footing is 550 mm. The concrete cover is 50 as calculated previously. And then the bar diameter, we use 12 mm rebar at the moment. That gives you the effective depth of 494 mm. We will do the similar to determine the effective depth in the minor axis. Except that you will have to consider 1 additional bar size due to the main reinforcement. Let's say this is your main reinforcement. Your secondary reinforcement will go this way. To determine the effective depth in the minor axis, we are talking about the distance from the top surface of the peg footing to the centroid of the secondary reinforcement. This is calculated by having the thickness of the peg footing minus the concrete cover minus the size of the main reinforcement and minus half size of the secondary rebar. The thickness of the peg footing 550, concrete cover 50, the bar diameter we assume equals to 12 at the moment, and you get slightly smaller effective depth in the minor axis. After that, we will proceed with determining the reinforcement bar in the major and the minor axis based on these 3 standard equations. You've seen these equations before in the design of most of the structural element of reinforced concrete structure, including the beam, slab, staircase. The foundations is no exemptions. Since we want to determine the moment, and then based on the moment, determine the AS required. First, we determine the limiting K here. Use this formula. You have the total moment calculated divided by FCK, which in this case, your FCK is equals to 30 Newton per mm square. 30 Newton per mm square is the minimum concrete grade for the foundations. You should not use concrete grade less than 30 for a typical foundation. And then you have B and D square. This you will need to be very careful. The B and the D used in the major and the minor axis differs. If you use them wrongly, you don't get the correct K. And when the K is incorrect, you don't get the right lever arm Z, and as a result, your amount non-reinforcement bar acquired is not correct. Let us first deal with the major axis. The main reinforcement bar resisting the moment in the major axis is here, along the longer span of the peg footing. Your B should be here, which is 2.2 meter for the major axis. As for the D, we are referring to the effective depth for the major axis. If you calculate the K for the minor axis, use the moment in the minor axis. FCK, it will be the same, which is 30. Your B now here, it will be 2.4 meter. Why is it so? If you look at the peg footing, the secondary reinforcement will go in these directions. If you view from this side, it will look something like this. You will have main reinforcement near to the soffit and secondary reinforcement here. Your B is referring to this, which will be the longer span. Therefore, it is equals to 2.4 meter. As for the D, you use the D from the minor axis. Get your K. You found that the K is less than 0.167. That means both sides do not require the compression reinforcement. Normally, you will expect the design of a typical peg footing does not require any compression steel bar. Why is it so? This is because the effective cross-sectional area of a peg footing is normally relatively large as compared to the moment acting onto it. The moment is one of the issues that can lead to the failure of a peg footing, but it is not the most critical one. More critically, the design of the peg footing is influenced by the shear resistance. In order to ensure sufficient shear resistance, normally we will provide a relatively thick peg footing. Due to a relatively large thickness, this gives you a relatively large effective depth against the moment. If this happens, then normally you don't need any compression rebar. Now let us proceed. We need to determine the lever arm Z here. Use the K calculated in the major and the minor axis to determine the Z. Check the ratios 0.983 and 0.986. This is greater than 0.95D. When it is more than 0.95D, you will use 0.95D. That means the calculated Z here is equals to 0.95 multiply the D in the major and in the minor axis. Having your Z determined, now we're going to calculate the AS required. Using this formula, you have the moment, the total moment in the major and in the minor axis, divided by 0.87 FYK and Z. FYK in this case is equals to 500 Newton per mm square, and the Z we have calculated previously. that give you the AS required 1535 and 1373 mm square. Then you're going to propose sufficient amount of reinforcement bar so that the AS provided is greater than the AS required. Let us first try a sling pass to the AS required. We propose 14 units of H12 mm rebar in the major axis, and then 13 units of H12 mm rebar in the minor axis. The total rebar area here are slightly larger than what is required. Therefore, as far as the moment is concerned, this proposed amount of reinforcement bar is adequate for both major and the minor axis. Then, don't forget to check the AS maximum and AS minimum. Let us first deal with the AS maximum. AS maximum is defined by 4% of the cross-sectional area of that particular section. For the reinforcement in the major axis, your main reinforcement, it will be here. Now your cross-sectional area, it will be this. Your AC here is calculated based on the height of the peg footing multiply the width, which is equals to 2.2 meter. That gives you the AS maximum in the major axis equals to this. As for the AS maximum in the minor axis, your reinforcement bar, it will be in these directions. The cross-sectional area, it will be this. That means your AC is determined by the thickness of the peg footing multiply the width here, which is equals to 2.4 meter, giving you another AS maximum. Check the amounts of reinforcement bar provided not exceeding the AS maximum, and the outcomes end up to be quite okay. You know that the peg footing is not over reinforced. Next, we will look into the AS minimum. AS minimum is calculated based on two methods. The first one is due to this formula that you can obtain from Eurocode 2. You will need FCTM, which you can get it from table 3.1 in Eurocode 2. This is table 3.1. Your FCTM is this row. Grade 30 concrete will have 2.9 FCTM. FYK equals to 500, and then multiply the B and D. The D, it will be based on the effective depth for the major and the minor axis. As for the B, for the major axis, the B is equals to 2.2 meter. As for the minor axis, the B equals to 2.4 meter. Bring this BD to the opposite and they behave in the mode of multiplications. You will get your AS minimum. And then you may use the ratio for the BD, which is determined on the basis of the concrete grade. AS min for grade 30 concrete is about 0.15%. So we use this 0.15% multiply the BD. Based on the two AS min obtained, a bigger value is used. And we use this to check against the AS provided. As you can see here, the proposed amount of reinforcement bar is insufficient based on the requirements for the AS minimum. The purpose of AS minimum is to control cracking. This means that the proposed amount of reinforcement bar, although it is sufficient to take the moment, but it is not sufficient to control cracking. Therefore, you will need to add the amount of reinforcement bar so that you have your AS provided greater than the AS minimum. Now, instead of providing 14 units, you need to add more reinforcement bar to become 15 units of H12 rebar in the major axis and 16 units of H12 rebar in the minor axis. Now you will have both the AS provided, fulfilling the AS required, as well as the AS minimum. Up to this stage, now you have your amount of reinforcement bar more or less confirmed, at least from the aspects of the moment resistance, the crack control, and not to be over reinforced. We will proceed later to deal with the shear loads. That will be covered in the following videos. Stay tuned.